After the dinosaurs disappeared, Earth did not become calm. That is the first thing to understand about Titanoboa. The giant snake did not slide through a world full of Tyrannosaurus, Triceratops, or giant long-necked dinosaurs. It did not hunt people. It did not survive secretly into the modern Amazon. It belonged to a different chapter, a hot, wet, restless chapter, after the asteroid had already ended the reign of the non-avian dinosaurs. The old Mesozoic world was gone, but the new world had not yet settled into anything familiar. The planet was rebuilding. Forests were returning. Rivers were reshaping tropical lowlands. Mammals were still mostly small. Crocodilian relatives, turtles, fishes, and reptiles filled the water. In that post-dinosaur heat, in the swampy ecosystems of what is now northern Colombia, one of the largest snakes ever discovered became a top predator. Titanoboa is easy to turn into a monster. The name almost invites it. A snake longer than a school bus, heavier than many modern reptiles, moving through a dark tropical river with a body thick enough to make modern anacondas seem modest by comparison. For a thumbnail, it is perfect. The largest snake in Earth's history, a predator from a lost jungle. An animal so large that it feels like a mistake in the fossil record. But if we only treat Titanoboa as a monster, we miss what makes it scientifically powerful. Titanoboa is not just a giant snake. It is a clue. It tells us about the world after the dinosaur extinction, about tropical climate, about reptile physiology, about ancient wetlands, about how ecosystems recover after mass extinction, and about how life fills empty spaces when the old rulers are gone. The story begins not with a living snake, but with bones and coal. Titanoboa cerrejonensis was found in the Cerrejón Formation of Colombia, one of the most important windows into the Paleocene tropics. Today, Cerrejón is famous as a coal mine, but the rocks preserve something much older than industry. A rainforest world from roughly 58 to 60 million years ago, only a few million years after the asteroid impact that ended the Cretaceous period. Fossils from this formation revealed plants, turtles, crocodilian relatives, fishes, and the remains of a snake so large that paleontologists had to rethink what a tropical snake could become under the right conditions. At first, the fossils were not a complete skeleton curled perfectly in stone. Fossil snakes rarely give us that kind of gift. Much of what scientists had were vertebrae and ribs, the repeated bones of a long body. But in snakes, vertebrae are information-rich. They can reveal relationships, size, and body proportions when compared carefully with living and fossil snakes. The vertebrae of Titanoboa were enormous. When researchers scaled them against modern boas and anacondas, the animal that emerged from the measurements was staggering. About 13 meters long in the original estimate, over 40 feet, and likely around a metric ton or more in mass. Some popular reconstructions describe it as about 45 to 50 feet long, depending on the method and display. The exact number is less important than the biological fact. This was a snake at the upper edge of what snakes are known to have achieved. That size should make us pause, not just stare. A snake is not a dragon. It is not built like a mammal. It does not carry its body on legs. It moves by muscle waves, ribs, belly scales, friction, water support, and terrain. A snake that large would not behave like a fast-moving monster chasing people across dry ground. Titanoboa was almost certainly an animal of water and wet ground, a giant of rivers, swamps, and tropical floodplains. To imagine it properly, do not picture a creature sprinting through open plains. Picture a dark channel under a thick rainforest canopy. Picture warm water barely moving. Picture floating plants, muddy banks, the eyes of crocodiliforms at the surface, turtles sliding from logs, large fish moving below. Then imagine a body as thick as a barrel shifting almost silently through the brown water. That environment matters because Titanoboa's size was not just a personal achievement. It was an ecological result. Giant snakes do not appear in isolation. They require prey, habitat, climate, and enough evolutionary opportunity for a lineage to expand into that role. The Paleocene tropics of Cerrejón seem to have provided all of those things. The world was warm. The region was wet. The ecosystem was rich in aquatic and semi-aquatic animals. With non-avian dinosaurs gone, many food webs had been reorganized. Large reptiles remained important in tropical ecosystems, but the balance had changed. Titanoboa was part of that new balance. The phrase "after the dinosaurs" is important, but it can mislead if we treat it as a simple empty world story. The asteroid did not wipe out all life, and it did not leave every ecological role vacant. Birds survived. Crocodilian lineages survived. Turtles survived. Lizards and snakes survived. Mammals survived. Fishes survived. Plants were damaged but recovered. The Paleocene was not a blank page. It was a damaged page with many old lines still visible, and many new ones beginning. Titanoboa did not rise in a world with no competition or no complexity. It rose in a recovering world where tropical ecosystems were becoming dense, productive, and strange. What did Titanoboa eat? This is where monster stories often go too far. Titanoboa did not eat dinosaurs. It lived after the non-avian dinosaurs were gone. It did not eat humans. Humans were tens of millions of years in the future. It did not battle movie-style prehistoric creatures for spectacle. The best answer is more grounded and more interesting. Titanoboa likely hunted in and around water, and its diet probably included large aquatic prey. Early interpretations compared it to modern anacondas and suggested it could prey on crocodiliforms and turtles from the Cerrejón ecosystem. Later skull evidence has also suggested strong adaptations for catching fish, pointing to a more fish-heavy ecology than a simple crocodile-eating monster image. The most careful way to say it is that Titanoboa was a giant aquatic or semi-aquatic predator in a wetland ecosystem, likely capable of taking large fish and perhaps other vertebrates such as crocodilian relatives or turtles when opportunity allowed. That may sound less dramatic than it ate crocodiles for breakfast, but it is better science and actually more vivid. A huge snake does not need constant cinematic battles to be terrifying. It can be an ambush predator, waiting in warm water, using cover, patience, and sudden force. Modern large constrictors do not live like action villains. They are efficient, patient predators. A giant snake in a Paleocene swamp would not need to chase everything. It could wait. It could use water to support its mass. It could strike from concealment. It could pull prey into the river environment, where its size became an advantage rather than a burden. Its relationship with crocodilian relatives is especially interesting. The Cerrejón ecosystem included crocodiliforms, some smaller than modern large crocodiles, others part of a diverse post-dinosaur reptile community. In a tropical wetland, predator and prey roles can be complicated. Young crocodilian relatives might be prey for a giant snake. Small snakes or other animals might be prey for crocodilians. Large fish could feed multiple predators. A turtle might be safe from some hunters but vulnerable to others. Titanoboa was likely near the top of the food web. But food webs are not simple ladders, they are networks. The same ecosystem could contain multiple predators, scavengers, opportunists, and prey species whose roles change with size, age, season, and habitat. The size of Titanoboa also tells us something about temperature. But again, this has to be handled carefully. Snakes are ectotherms. Their body temperature and metabolism are strongly influenced by the environment. Large ectotherms are common in warm climates because warmth helps support activity, digestion, growth, and reproduction. When Titanoboa was described, researchers argued that a snake of this size implied very warm equatorial temperatures in Paleocene South America, perhaps warmer than modern tropical conditions. That idea became one of the most famous scientific messages of Titanoboa, the giant snake as a living thermometer for an ancient greenhouse world. But science is not a poster slogan. Estimating ancient climate from body size is difficult. Living animals are shaped by many factors, not only temperature. Prey availability matters, habitat matters, evolutionary history matters, physiology matters, the fossil sample matters, the scaling method matters. Later discussions have debated how directly Titanoboa's size can be translated into a precise temperature estimate. The safest and most honest conclusion is not that Titanoboa gives us one exact number carved in stone. It is that Titanoboa fits a picture of a very warm, humid Paleocene tropical ecosystem. Its gigantic size makes the most sense in a hot world, but the animal should be understood as one line of evidence among many, not a single thermometer with no error bar. Even with that caution, Titanoboa remains a powerful climate clue. The Paleocene was part of an interval of generally warm global climate. Polar ice sheets were absent or reduced compared with today's world, and tropical ecosystems existed under greenhouse conditions. In Cerrejón, fossil plants and animals point to a humid tropical rainforest environment. Large reptiles, giant turtles, crocodiliforms, and Titanoboa together suggest a world where heat and water allowed ectothermic predators to become enormous. If you want to understand Titanoboa, you have to feel the air around it. Heavy, wet, hot, full of insects, plant decay. muddy water, and the pressure of a rainforest that had grown back after global catastrophe. The post-dinosaur timing is one of the most fascinating parts of the story. The asteroid impact occurred about 66 million years ago. Titanoboa lived roughly 58 to 60 million years ago. That means it was not immediate aftermath, but it was still early in the recovery of the Cenozoic world. The ecosystems of the Paleocene were experiments in rebuilding. Mammals were diversifying, but many had not yet reached the large forms that would come later. Birds were evolving into new roles. Crocodilian relatives and turtles remained important in warm aquatic environments. Snakes, already present before the extinction, had new opportunities in changing food webs. This raises a key question. Why did a giant snake appear after the dinosaurs? Part of the answer may be ecological opportunity. The extinction of non-avian dinosaurs removed many large terrestrial animals and reshaped ecosystems. In tropical wetlands, the absence of large dinosaurian predators did not mean reptiles vanished. It meant other reptiles could occupy important roles. Crocodiliforms, turtles, and snakes persisted and diversified in different ways. Titanoboa was not a dinosaur replacement in a simple one-for-one sense. It was a predator that flourished in a specific warm, wet ecosystem where its body plan worked extremely well. Another part of the answer is climate. A giant ectotherm needs heat. Today's largest snakes, like green anacondas and reticulated pythons, live in warm regions. They do not reach Titanoboa's size, but they show the general pattern. Giant snakes are tropical animals. A cooler world would make a Titanoboa-like body more difficult to support. A world with warm, stable, productive wetlands makes it more plausible. That does not mean warmth automatically creates giant snakes. It means warmth removes one important barrier and allows other factors, such as prey and habitat, to matter. A third part of the answer is water. Water changes the rules for large bodies. On land, a huge limbless body faces serious mechanical challenges. In water, buoyancy helps support mass. Modern anacondas are strongly aquatic, and they use water as part of their hunting and movement strategy. Titanoboa likely benefited from a similar principle at much greater scale. A swamp, river, or floodplain would allow such a huge snake to move, hide, thermoregulate, and ambush prey more effectively than dry open land. The animal belongs to a wet world. This is why the best Titanoboa scene is not a monster rising from nowhere. It is a natural history scene. A Paleocene river flows through a rainforest. The canopy is dense, the air is warm enough to feel heavy. The water is stained dark by plant material. A turtle moves near the bank. Crocodiliforms wait in shallows. Large fish turn under the surface. Birds may call above, though not in the way modern tropical birds dominate our imagination. In the mud, a huge snake has been still for so long that it seems part of the river. Then the body moves. Not fast at first, not theatrically. Just enough to remind everything nearby that the river itself has a predator. Could Titanoboa crush prey? As a giant boid snake, it was related to constrictors, and constriction would likely have been part of its predatory toolkit. But we should avoid pretending we know every detail of its hunting behavior. Fossils do not preserve a chase. They do not preserve a strike. They do not preserve how often the snake fed or what its favorite prey was. They preserve anatomy, environment, associations, and clues. From those clues, scientists reconstruct probabilities. Titanoboa was certainly large enough to be dangerous to many animals in its ecosystem. It likely used ambush and water. It likely ate large aquatic prey. But the most honest version leaves room for uncertainty. Uncertainty is not weakness. It is part of why paleontology is interesting. A fossil animal is not a movie character with every scene recorded. It is a puzzle assembled from bone, rock, chemistry, comparison, and living analogs. With Titanoboa, the vertebrae tell us size. The skull material gives clues about diet and relationships. The Cerrejón Formation tells us habitat. Associated fossils tell us about the ecosystem. Modern boas and anacondas tell us what large constrictors can do. But they cannot simply be copied onto Titanoboa. The animal was related, not identical. The world was similar in some ways, radically different in others. One of the most common questions is whether a snake like Titanoboa could exist today. The answer is probably no, at least not under current conditions in any straightforward sense. Modern Earth has large tropical wetlands and large snakes, but we do not have Titanoboa. That absence likely reflects several factors. Global climate today is different from the Paleocene greenhouse world. Modern tropical ecosystems have different prey communities, different competitors, different habitats, and human pressures layered on top. Even if a modern anaconda lives in water and can become enormous by today's standards, it is not living in the same climate regime or ecological world as Titanoboa. This does not mean Titanoboa was impossible by modern biology. It means Titanoboa was possible under its own historical conditions. Animals are not just bodies. They are bodies and worlds. Change the world and the same body may no longer work. A 15-meter-ish snake would need enough warmth, enough prey, enough suitable aquatic habitat, and enough evolutionary history to get there. Today's Earth does not seem to provide that combination, and there is no credible evidence that Titanoboa or anything like it survives in hidden swamps. The fossil record gives us a real giant. We do not need a modern myth. The myth persists because giant snakes occupy a powerful place in human imagination. Snakes are already unsettling to many people because they move without legs, strike quickly, and hide well. Make one enormous, and the human brain immediately turns it into a monster. But the scientific Titanoboa is more interesting than the mythic one. A monster only scares us. Titanoboa explains a world. It makes the Paleocene tangible. It shows what can happen when climate, wetlands, prey, and reptile evolution align. It turns the recovery after the dinosaur extinction into something we can see and feel. The Paleocene world is often overshadowed by what came before and after. Before it, the dinosaurs dominate the imagination. After it, the Eocene brings warm forests, early whales, strange mammals, and more familiar Cenozoic stories. The Paleocene sits in between, like a recovery room after a planetary trauma. But recovery rooms are where some of the most important biological shifts happen. The old giants are gone. Survivors are expanding. New food webs are forming. The world is not empty, but it is unsettled. Titanoboa belongs to that unsettled creativity. It is also a reminder that the end of the dinosaurs did not mean mammals instantly ruled everywhere. In many popular versions of Earth history, the asteroid hits, dinosaurs disappear, mammals rise, and the rest is inevitable. But reality was less simple. Mammals diversified after the extinction, but reptiles remained extremely important, especially in warm environments. Crocodilians, turtles, lizards, and snakes did not step aside. In some tropical ecosystems, reptiles continued to dominate aquatic and semi-aquatic predatory roles. Titanoboa is a perfect example. The post-dinosaur world was not automatically a mammal world. It was a survivor world. That survivor world had its own atmosphere. Imagine the first millions of years after the Cretaceous-Paleogene extinction. Not as silence, but as rearrangement. Forests return. Rivers fill with new communities. The ancestors and relatives of modern groups spread into spaces left by extinct lineages. Some animals remain small. Others become surprisingly large. In the tropics, where warmth and productivity can be intense, evolution explores sizes and ecological roles that feel almost exaggerated. Titanoboa was not a leftover dinosaur age monster. It was a Cenozoic experiment in reptilian gigantism. Its discovery also changed what scientists knew about ancient tropical South America. Fossils from tropical rainforests are difficult to find because warm, wet environments often destroy organic material and because dense vegetation hides exposures. Cerrejón is valuable because coal mining exposed rock layers that preserve a rare window into Paleocene rainforest life. Without mining exposure and the fieldwork of paleontologists, Titanoboa might still be unknown. This is important because our picture of ancient life is shaped by where fossils can be found. There may have been many remarkable tropical animals whose records were never preserved or never exposed. Titanoboa therefore stands for more than one species. It represents the hidden history of the tropics. For a long time, much of the fossil story was easier to tell from temperate regions, deserts, badlands, and places where bones weather out visibly. Tropical ecosystems, despite being biodiversity hotspots today, are often underrepresented in deep-time fossil records. Cerrejón gives us a rare fossil rainforest with giant reptiles, plants, and aquatic communities. Titanoboa is the celebrity, but the ecosystem around it is the true treasure. That ecosystem included huge turtles and crocodiliforms, animals that make sense in a warm aquatic world. Turtles can thrive in wetlands, and some fossil turtles from Cerrejón were large and heavily shelled. Crocodiliforms are diverse, occupying aquatic and semi-aquatic roles. Large fish move through the rivers. Plants form dense forest. The environment was not a backdrop painted for Titanoboa. It was a functioning community, and Titanoboa was part of it. A predator that large requires a web beneath it. If the web fails, The predator fails. This is why questions about Titanoboa's diet matter. If it ate mostly fish, it tells us about abundant large fish and aquatic ambush strategies. If it also took crocodilian relatives or turtles, it tells us about predator-prey interactions in a reptile-rich wetland. Either way, it was not feeding on fantasy. It was feeding on the products of a real ecosystem. A giant predator is an ecological statement. The habitat was productive enough to support it. The climate was warm enough to allow it. The prey base was rich enough to sustain it. The evolutionary lineage had the tools to exploit it. Its body size also raises questions about metabolism and digestion. Large snakes today can eat large meals and then digest them over extended periods. Digestion in ectotherms is temperature dependent. A warm environment helps. For a snake the size of Titanoboa, feeding events may have been infrequent but substantial, depending on prey type. Again, we should not invent exact schedules. We do not know that it ate a crocodilian every certain number of weeks, but we can infer that its life was probably built around patience, bursts of feeding, and long, metabolic processing, much like large constrictors today, scaled into a warmer ancient world. Movement is another interesting question. On land, Titanoboa would have been impressive but likely not agile in the way movie monsters are shown. In water, its body becomes more plausible. The river supports mass. The snake can push against water and submerged surfaces. It can hide its bulk. It can approach prey with less mechanical strain. A giant snake's horror is not speed across open ground. It is invisibility in the wrong medium. If you are a fish, turtle, or small crocodiliform in a muddy Paleocene channel, the danger is not that Titanoboa chases you like a mammal. The danger is that you do not know which shadow is river and which shadow is snake. There is a quiet pressure in that image, and it is the pressure this documentary should carry. Not cheap horror, not screaming victims, not fake battles with dinosaurs. A humid world, a recovering biosphere, a giant predator moving through brown water. The fear comes from scale and reality. Titanoboa was real. Its fossils are real. Its world was real. That is stronger than myth. The story also helps explain why reptiles can become so large under certain conditions. Ectothermy is often misunderstood as weakness. Because reptiles rely heavily on external heat, people sometimes imagine them as limited. But ectothermy can also be efficient. Reptiles often require less food than similarly sized warm-blooded mammals because they do not maintain constant high body temperature internally in the same way. In a warm environment, a giant ectothermic predator can be a powerful ecological solution. Titanoboa's size was not a violation of reptile biology. It was one of the most extreme expressions of it. But size has costs. A giant snake needs appropriate temperatures. Too cold and it cannot function well. Too hot and overheating may become a problem. It needs water or suitable habitat to move and hunt. It needs prey large enough and abundant enough. It needs reproductive success, not just individual growth. A single giant animal is a spectacle. A species requires a population. Titanoboa was not just one freak individual. Fossil material indicates multiple individuals, which means this was a real ecological population, not one impossible outlier. This makes Titanoboa more scientifically important. A population of giant snakes means the environment repeatedly produced and supported such bodies. That tells us the Saron ecosystem was not merely warm once or productive once. It had conditions that could sustain giant boyed snakes over evolutionary time. That is a richer message than the size record alone. Another question people ask is how Titanoboa compares to modern anacondas and pythons. Modern green anacondas are among the heaviest living snakes, adapted to aquatic habitats in South America. Reticulated pythons can reach extreme lengths in Southeast Asia. Both show how large snakes live today. Warm climates, ambush, powerful bodies, and often a close connection to water or dense cover. Titanoboa dwarfed them in reconstructed mass and length, but it was not unrelated in concept. It was not an alien serpent. It was an extreme member of a recognizable evolutionary theme, giant constricting snakes in warm, prey-rich environments. The comparison should not be exaggerated into fantasy. A modern anaconda is not a baby Titanoboa. A python is not a failed Titanoboa. They are separate animals with their own evolutionary histories. But the comparison helps us understand scale. If a modern anaconda can already feel impossibly large to a human observer, Titanoboa pushes that body plan into a range where the animal becomes part of the landscape. A modern giant snake is a predator. Titanoboa was a habitat-level presence. Could climate alone explain its size? Probably not. Climate makes size possible. Ecology makes it useful. In a hot world without enough prey, a giant snake would starve. In a prey-rich world that is too cool, a giant snake would struggle physiologically. In a warm and productive wetland, the pieces align. Titanoboa teaches us to avoid single-factor explanations. Just as mass extinctions are multi-causal, gigantism is multi-causal. The animal is the intersection of heat, food, water, ancestry, competition, and time. Its extinction is less famous than its life, and we should be careful here too. We do not have a dramatic final scene for Titanoboa. We should not claim that one cold year killed it, or that mammals hunted it, or that it vanished in one sudden event unless evidence supports that. More likely, as climates changed, ecosystems shifted, and evolutionary communities reorganized through the Cenozoic, the specific conditions that allowed Titanoboa to thrive disappeared. Giant specialized animals are often vulnerable when their habitat, prey base, or climate window changes. Titanoboa belonged to a particular world. When that world changed, its kind did not continue. This is one of the great themes of paleontology. The most spectacular animals are often not timeless monsters. They are precise answers to extinct worlds. Change the question, and the answer disappears. Titanoboa was a perfect answer to a hot Paleocene tropical wetland. It was not a universal snake that could dominate any Earth at any time. It ruled because the world let it rule. That perspective makes the animal more beautiful. A monster is just big. An extinct organism is specific. It has a time, a place, a climate, a community, a lineage, and a set of pressures that shaped it. Titanoboa was not the giant snake in abstract. It was Titanoboa cerrejonensis of the Paleocene neotropics, known from the Cerrejón Formation, part of a rainforest ecosystem that existed after the dinosaurs, but before the rise of many modern mammal-dominated worlds. Its name carries a place, a moment, and a scientific story. The scientific story is still developing. Paleontology changes as new fossils are found and old fossils are re-examined. Skull material can change interpretations of diet. New giant snake discoveries may complicate rankings of size. Better climate models may refine what Titanoboa says about Paleocene temperatures. That does not make the original discovery less important. It means the animal remains part of an active scientific conversation. Good science is not frozen at the moment of discovery. It keeps testing the story. For a documentary, that is important. We should not present Titanoboa as if every detail is settled. We can be confident that it was enormous, Paleocene, Columbian, associated with warm tropical wetland ecosystems, and among the largest snakes ever known. We can explain that its size likely relates to climate and ecology. We can say it probably preyed on large aquatic animals, with evidence pointing especially toward fish and possibly other vertebrates. But we should avoid false certainty about exact behavior. The difference between science and monster fiction is not that science has no imagination. It is that scientific imagination stays tied to evidence. That evidence makes Titanoboa one of the best gateways into the world after the dinosaurs. Most people imagine the post-extinction world as mammals waiting to take over. Titanoboa forces a different image, a reptile-dominated tropical wetland where the largest predator may have been a snake. That is a richer, stranger, more accurate vision. The end of one age did not immediately create the world we know. It created experimental ecosystems, survivor communities, and new giants. There is also something almost poetic about a snake ruling after the dinosaurs. Dinosaurs are associated with legs, speed, height, herds, claws, horns, and open landscapes. Titanoboa is the opposite kind of giant. Low, silent, limbless, hidden, aquatic, patient. It does not dominate by towering over the land. It dominates by blending with the water. It represents a different kind of power. Not the thunder of a sauropod or the sprint of a theropod, but the slow authority of a river predator that only needs one perfect moment. That power belonged to a planet still healing. The asteroid impact had removed the most famous giants, but life did not stay small. In some places, in some lineages, under some conditions, size returned quickly. Not dinosaur size, not mammoth size, but reptile size in a different form. Titanoboa shows that recovery after extinction can produce unexpected rulers. Evolution does not replace one dynasty with a planned successor. It experiments. Sometimes, the experiment is a snake so large that its vertebrae look almost unbelievable. The world of Titanoboa was not safe, but it was alive. This matters emotionally. After mass extinction, we often imagine emptiness. But recovery is not emptiness. It is struggle, opportunity, instability, and renewal. The Paleocene rainforest of Sarahan was part of that renewal. Plants grew, rivers flowed, fish diversified, turtles and crocodiliforms moved through wetlands. Snakes evolved into massive predators. Life did not restore the Cretaceous. It built something else. That something else is the heart of Titanoboa's story. It is not a dinosaur story. It is a recovery story, a climate story, a tropical ecology story. A story about how a planet that had lost its most famous animals still had the capacity to generate astonishing new forms. Titanoboa ruled not because it escaped the dinosaur extinction, but because it belonged to the world that came after. So how big was Titanoboa really? Big enough to stretch more than 40 feet in many reconstructions. Big enough to weigh roughly around a ton or more. Big enough that its vertebrae forced scientists to announce one of the largest snakes ever discovered. But numbers alone are not the point. The real size of Titanoboa is ecological. It was large enough to tell us the Paleocene tropics were hot, wet, productive, and capable of supporting enormous reptilian predators. Its body is a measurement of a lost climate. What did it eat? Most likely large aquatic prey, with evidence supporting fish as important and with the possibility of crocodiliforms or turtles in its food web. The exact menu is uncertain, but the feeding world is clear. Rivers and swamps full of animals large enough to support a giant ambush predator. Why did giant snakes appear after the dinosaurs? Because the post-extinction world was not empty, but it was open to new ecological arrangements. Warm climate, wet habitat, prey availability, reptile survival, and evolutionary opportunity combined. Titanoboa was not a random monster. It was a logical product of its world. What does it tell us about ancient climate? It tells us that the Paleocene tropics were extremely warm and humid, though we should not pretend one snake gives us a perfectly exact temperature. It supports the image of a greenhouse world where ectothermic animals could achieve extraordinary size. Could a snake like Titanoboa exist today? Not realistically, based on current evidence. Modern snakes can become huge, but no living species approaches Titanoboa's reconstructed scale. Today's climate, ecosystems, prey communities, and human-altered habitats are different. Titanoboa belongs to the Paleocene, not to hidden modern swamps. And that is enough. We do not need Titanoboa to be alive today. The real animal is more interesting than any rumor. It lived in a world after the dinosaurs, when Earth was still rewriting its ecosystems. It moved through tropical rivers in a climate warmer than ours, among giant reptiles and dense rainforests. It was not a dragon, not a myth, not a survivor from a lost monster age. It was a snake built by evolution, climate, and ecology, and that is far more powerful. If you strip away the sensational image, Titanoboa becomes even more impressive. It is a reminder that the history of life is not a straight march from primitive to advanced, or from dinosaurs to mammals to humans. It is a branching, unstable, unpredictable history full of worlds that feel impossible until fossils prove they were real. A coal mine in Colombia opened a window, and through that window came a snake large enough to change how we imagine the Paleocene. Titanoboa ruled a world we almost never picture. Not the dinosaur world, not the Ice Age world, not the modern Amazon, but the hot, wet, post-dinosaur tropics of deep time. Its story begins after extinction and ends before the world becomes familiar. That is why it feels so strange. It belongs to the in-between. And maybe that is the best way to understand it. Titanoboa was an in-between giant. After the dinosaurs, before the rise of many modern ecosystems, before humans, before grasslands became widespread, before the Amazon as we know it, there was a tropical world of coal forests, rivers, turtles, crocodilian relatives, fishes, and a snake almost too large to believe. It was not a monster movie. It was Earth history. The discovery itself also has a human side that is worth remembering. Titanoboa did not announce itself as a complete giant serpent. Its bones were pieces in a landscape of coal, mudstone, heat, and heavy fieldwork. Fossils from tropical settings can be stubborn. They may be fragmentary, weathered, scattered, or hidden in industrial exposures. The recognition that those huge vertebrae belonged to a snake required comparison, patience, and a willingness to see something unlikely in the rock. At first glance, giant fossil vertebrae from a coal mine might not immediately make a person think of a snake, because our mental image of snakes is often shaped by modern species. But paleontology often begins when something does not fit the expected scale. One oversized bone can be the first clue that an entire ecosystem was stranger than anyone imagined. The name Titanoboa cerrejonensis says a lot in two words. Titanoboa combines the idea of a titan with a boa, signaling both size and relationship. Cerrejonensis ties the animal to Cerrejón, the place that preserved it. Scientific names can sound dry, but in this case the name is almost a compressed documentary, a titanic boa from Cerrejón. It tells you that the animal was huge, snake-like in a very particular lineage, and rooted in a specific fossil landscape. That matters because extinct animals should not float free as isolated monsters. They belong to localities. They come from formations, sediments, climates, and communities. Titanoboa is not only a body, it is a coordinate in deep time. The Cerrejón rainforest also helps correct a common misunderstanding about the tropics after mass extinction. People often imagine that the equatorial world would have recovered quickly, and simply because warm regions are productive today. But ancient tropical ecosystems had their own recovery histories. The fossil plants of Cerrejón show one of the earliest known neotropical rainforest ecosystems after the dinosaur extinction. That means Titanoboa was part of a broader story about rainforest development. The snake was not merely lurking in a generic swamp. It inhabited a world where tropical plant communities, river systems, and reptile-dominated wetlands were forming new Cenozoic patterns. Its size draws attention, but its environment gives it meaning. There is also a deeper climate question hiding behind the animal. In today's world, the tropics are warm, but there are still limits. A giant ectotherm must avoid both cold and overheating. If the Paleocene tropics were extremely hot, how did large reptiles function without cooking? The answer is probably behavioral and environmental complexity. Water offers thermal buffering. Shade from rainforest canopy matters. Activity patterns can shift by time of day. Large bodies warm and cool differently than small bodies. Titanoboa's existence does not mean it spent every moment in exposed sunlight. A huge aquatic snake could use water, shade, mud, and depth as part of its thermal world. It was not simply big because hot. It was big in a habitat that could help manage heat. That detail matters because ancient climate was not a single number. Mean annual temperature is a useful concept, but animals live in days, nights, seasons, microhabitats, droughts, floods, sunny banks, shaded channels, and deep pools. Titanoboa's body existed in all of that variation. The question is not only how warm the Paleocene tropics were on average, but how those warm conditions interacted with water, forest cover, prey availability, and reptile behavior. The animal becomes a way to think about climate as lived experience, not just air temperature. A whole thermal landscape. The fossil record around Titanoboa also reminds us that predator size depends on prey size. A giant snake needs more than heat, it needs meals. The Cerrejón ecosystem contained large aquatic animals, and that is crucial. If the rivers had held only tiny prey, Titanoboa would not make ecological sense. Large fish, turtles, and crocodiliforms formed the kind of prey field that could support a huge ambush predator. Even if scientists continue to refine exactly how much fish versus other vertebrates Titanoboa ate, the broad point remains. Its world was not poor. It was productive enough to feed giants. There is a temptation to imagine Titanoboa as invincible. But no predator is invincible. Young Titanoboas, if they resembled other snakes in having vulnerable early life stages, may have been at risk from birds, crocodiliforms, large fish, or other predators. Eggs or juveniles would have faced different dangers than full-grown adults. A mature Titanoboa may have dominated many encounters, but a species is made of life stages. Paleontology often gives us the spectacular adult image, while ecology reminds us that survival begins small. Even the largest snake in Earth's history would have had to hatch or be born into danger, grow through vulnerable sizes, find food, avoid becoming food, and survive long enough to become the enormous animal we imagine. Thinking this way makes the animal more real. It had a life cycle. It did not appear as a giant. It grew, it shed skin, it digested, it rested, it reproduced. It probably spent long periods doing very little that would look dramatic on film. A real giant snake is not constantly attacking. It is conserving energy, choosing positions, responding to water levels and temperature, waiting for opportunity. The slowness is part of the power. In nature, dominance is not always loud. Sometimes it is the ability to wait longer than everything else. The world around it was also full of sound and smell, not just visual drama. A Paleocene swamp would have carried the smell of wet vegetation, decaying plant matter, mud, animal musk, and warm stagnant water. Insects would have been present. Leaves would have fallen into channels. Fish would have broken the surface. Crocodiliforms would have moved between water and bank. Rainstorms could change water levels. Seasonal pulses may have altered where prey gathered. A giant snake in that world would be part of a sensory landscape very different from a museum skeleton. Fossils give us bone, but imagination, disciplined by ecology, gives us habitat. The phrase, ruled after the dinosaurs, should therefore be understood in a specific way. Titanoboa did not rule the whole planet. It did not dominate every Paleocene ecosystem. It ruled, if we use that word, in its own tropical wetland world. That distinction keeps the story honest. Earth after the dinosaurs was not one uniform stage. Different regions had different climates, faunas, and recovery pathways. In some places, mammals became increasingly important. In some warm wetlands, reptiles remained major players. Titanoboa's kingdom was not Earth in total. It was a hot, river-cut, rainforest world in northern South America. There is strength in that specificity. General monster claims are cheap. A real ecological claim is better. In one of the earliest known neotropical rainforest ecosystems after the Cretaceous extinction, a snake reached extraordinary size and became part of the top predatory structure. That is more precise, and it is more astonishing. It tells us that the recovery of life was not only about mammals getting bigger, but about different lineages experimenting in different habitats. The Paleocene was not a straight road to us. It was a branching landscape of possibilities. Titanoboa also changes the emotional texture of the largest ever question. Records are exciting, but records can be unstable. A new fossil may rival an old one. A better estimate may shift a ranking. A fragment may be interpreted differently. If we only care about whether Titanoboa is number one forever, we miss why it matters. Even if future discoveries complicate the title, Titanoboa remains one of the greatest fossil snakes ever known and one of the most important clues to Paleocene tropical ecology. Its significance does not depend entirely on a trophy label. It depends on the world it reveals. That is useful for storytelling too. The title can say largest snake because that is the hook most viewers understand, but the script should lead them beyond the record. The goal is not to make people say, "That was a big snake," and leave. The goal is to make them say, "The world after the dinosaurs was far stranger than I thought." Titanoboa is the door. Paleocene ecology is the room. When we ask whether Titanoboa could exist today, we are really asking whether the modern world can still produce ancient extremes. The answer is not only about temperature. Modern habitats are fragmented. Large wetlands are altered by humans. Big predators are often pressured by habitat loss, conflict, and declining prey. Even if climate in some regions is warm enough for large snakes, the full ecological package is not the same. A Titanoboa scale animal would need space, prey, reproductive success, and long-term stability. Modern Earth is not just cooler in some relevant ways. It is also more crowded by us. That is why cryptid-style claims miss the point. A hidden Titanoboa would not be just one animal hiding in a river. It would imply a breeding population of giant snakes, a massive prey base, and a habitat capable of hiding and feeding them over generations. There is no good evidence for that. Paleontology gives us real giants without needing modern conspiracy. The ancient world is already stranger than rumor. In the end, Titanoboa is a story about scale, but not only physical scale. It is about the scale of time between the asteroid and the rainforest. The scale of climate warm enough to support giant ectotherms. The scale of ecosystem rebuilding after catastrophe. The scale of a predator so large that a single vertebra can change scientific imagination. It is also about the limits of certainty. We know enough to be amazed, and not enough to be arrogant. That balance is exactly what makes prehistoric ecology powerful. The goal is not to drain wonder by explaining it. The goal is to make wonder more accurate. Titanoboa becomes more impressive when we stop treating it as a movie monster and start treating it as a real animal from a real world. A movie monster can be any size the writer wants. Titanoboa had to obey physics, climate, anatomy, prey availability, and evolutionary history. It was not impossible, it was conditional, and the conditions were extraordinary. So when we picture Titanoboa, the best image is not a fantasy snake attacking everything in sight. It is a vast Paleocene wetland under a hot sky. The dinosaurs are already gone. The air is thick. The forest is dense. The river is dark. Somewhere beneath the surface, a giant body rests in the warm water, not as an invader from myth, but as a natural product of that world. It is not out of place. It is exactly where it belongs. The dinosaurs were gone. The tropics were hot, the rivers were alive, and in the water, almost silent, the largest snake in Earth's history waited.